All right. The first thing we're going to look at is the order of a matrix. And the order of a matrix in general is n by n, where m is the number of rows that the matrix has, and n is the number of columns that the matrix possesses. M by n matrix, always the number of rows by the number of columns. Okay. If two matrices are equivalent to each other, then two things have to be true. The order of matrix A has to be equal to the order of matrix B. That's to say that they must both have the same number of rows and columns, same number of rows and columns. That's one requirement for matrices to be equivalent to each other. Another requirement is that all of the corresponding entries of matrix A have got to be equivalent to the corresponding entries of matrix B. That's the only way two matrices can be equivalent to each other. Example, suppose I have this 2 by 2 matrix, matrix A. And I have this 2 by 2 matrix B. And suppose that we assume that these two matrices are equivalent to each other. If that's the case, what would be X, what would be Y, and what would be Z? Well, these matrices are equivalent to each other, then corresponding entries must be equal to each other. So X would have to be equal to 9. Y would have to be equal to -4. And Z would have to be equal to 7. Questions about that? All right, so again, for matrices to be equal, they both have to have the same order and corresponding entries must be equal to each other. Okay. All right, next thing is how do we add and subtract matrices?
Did you go over 6.2?
Well, there is a requirement. And the requirement is this right here. The inner dimensions of the matrices have to be the same in order for matrices to be even considered for multiplication. So these must be the same dimension here. So if I was to multiply an m by n by an n by p matrix, the order of my product matrix would be an m by p matrix. So if I have a 2 by 3 matrix, could I multiply a 2 by 3 matrix by a 3 by 5 matrix? Is that possible? That would be the case. It is possible since these inner dimensions are the same. What would be the dimension of my product matrix? Well, this would give me a 2 by 5 product matrix. Now, could I flip this around? Could I take a 3 by 5 matrix and multiply it by a 2 by 3 matrix? Is that possible? These are not the same. These inner dimensions are different. And because these inner dimensions are different, this product is impossible. Impossible. Cannot multiply those matrices together like that. Any questions what the requirement is for us to be able to multiply matrices together? Now, this, ladies and gentlemen, what I just went over here ironically, is not the requirement for adding or subtracting matrices together. It's the requirement for multiplying matrices together. So this is not correct here. And we will come back and revisit multiplication a little bit later on. This is for multiplying matrices together. In order to multiply matrices together, the inner dimensions have to be the same. In other words, the number of columns of the first matrix must be equal to the number of rows of the second matrix. If these dimensions are the same, then it's legal to multiply the matrices together. If these inner dimensions are not the same, we cannot multiply the matrices together. Okay. What I really wanted to focus on is how do we add and subtract matrices. So I will get back to that now, but we'll visit this in a couple of minutes a little later on. Come back to multiplication. So what is the requirement in order to be able to add or subtract matrices? Well, what is required is that the matrices must have the same order. Gotta be the same order. So like you could take a 2x2 matrix and you could add to it a 2x2 matrix to get a 2x2 matrix. You could take a 5x5 matrix and add to it a 5x5 matrix and get a 5x5 matrix. Same thing for subtraction. You could take a 6x6 matrix and you could subtract off, but it has to be a 6x6 matrix also to get a 6x6 difference matrix. Okay. So the order must be the same in order to add or subtract matrices. You cannot take a 2x3 matrix and add it to a 3x2 matrix. This is impossible. In order to add or subtract matrices, the orders must be identical for all the matrices. And that kind of stands to reason why that must be the case. Intuitively kind of makes sense. So if the order of some matrix A is equal to the order of some matrix B, and let's say that both these matrices are of the same order of m by n, then how do we actually add these matrices together here? Well, to actually add these matrices together and get a sum matrix here, we can only add together corresponding entries of the first matrix to corresponding entries of the second matrix. And this is for all I ranging from 1 to m, j ranging from 1 to n. So we can only add corresponding entries of matrices together, or this is also true for subtraction. If you were subtracting these matrices, you can only subtract corresponding entries of the matrices. All right, so let's look at an example. Suppose that matrix A is this 2x3 matrix consisting of these entries. And suppose matrix B is also a 2x3 matrix consisting of these entries. So what would be A plus B, matrix A plus B? Well, since these both have the same order, namely 2x3s, we can add them together. And we add them together by adding corresponding entries together. So the 1-1 entries get added together. The 1-2 entries get added together. The 1-3 entries get added together. The 2-1 entries get added together. The 2-2 entries get added together. And the 2-3 entries can be summed up. And then we get our sum matrix here, our 2x3 sum matrix, which looks like this. Now, since real number addition is commutative, this sum matrix would also be attainable if we took matrix B and added it to matrix A. So matrix addition, ladies and gentlemen, is commutative. In other words, A plus B is equal to B plus A. All right. But matrix subtraction is not commutative. Matrix A minus matrix B is not necessarily the same as matrix B minus matrix A. But that's true with addition and subtraction with real numbers. We know that subtraction is not commutative, but addition is commutative. All right. Any questions how we add matrices together? What if I was to take these two same matrices, A and B, instead of adding, suppose I was to subtract these two matrices. So what if I wanted to find matrix A minus matrix B? Well, all we got to do is just subtract all the entries from matrix B from the corresponding entries in matrix A. So this is to say I would get my 2 by 3 matrix by taking 1 and subtracting off -5. 2 subtract 4. 3 subtract a -3. 4 subtract a -2. 5 subtract 7. And 6 subtract 10. 1 subtract a -5 is 1 plus 5, which is 6. 2 minus 4 is -2. 3 minus a -3 is 3 plus 3 or 6. 4 minus a -2 is 4 plus 2, which is 6. 5 minus 7 is -2. And 6 minus 10 is -4. So that's how we subtract matrices. So adding and subtracting matrices is pretty simple. Provided we do have the same order matrices, we just add or subtract corresponding entries of the matrices to get our sum or our difference matrix. That's all there is to it. Any questions about that? Now, if A is an M by N matrix, then how would I multiply a matrix by some real number? Where K is just some real number. This is saying that K belongs to the set of real numbers. K is just any ordinary real number. Well, what is this new matrix K times A? Well, it's going to be a matrix where each entry of the matrix A gets multiplied by the real number K. Where these are elements of the matrix K times A. And this is true for all I less than or equal to M greater than or equal to 1, and for all J that roam between 1 and N. So multiplying a matrix by a real number is pretty simple. All you have to do is just multiply each entry of the matrix by that real number. And we'll look at an example. Suppose we're given matrix A, which is this 2 by 2 matrix. And suppose that K is equal to like -4. Suppose we wish to find KA, which is to say 4 times matrix A. -4 times matrix A. Which means nothing changes with the order of the new matrix. It's still going to be the same order. The only difference is that each entry of matrix A gets multiplied by -4. So this is gonna give me -12, -8, -20, and -24. There we go. Any questions how we did that there? Also, since multiplication is commutative, it would be true that K times A, matrix A, would be equal to matrix A times K. That's true. All right, I got a classwork for you. Classwork number 1. Today is the 6th day of April. Given matrix A is this 3x2 matrix. And matrix B is also a 2x3 matrix, 3x2 matrix, excuse me. Given those matrices, let's have you do this. I would like you to find A minus 7B. Go ahead and see if you can find A minus 7B, or A subtract 7B. Or matrix A subtract 7 times matrix B. See if you can find that. All right, so all I gotta do is multiply matrix B by 7 and subtract that off from matrix A, and this is what you would get here. Did anybody get that for a result?
Yeah.
All right. So adding and subtracting matrices is pretty simple. Matrices have to be the same order, and all you do is just add or subtract the corresponding entries. Multiplying a matrix by a real number is also pretty simple. All you have to do is make sure that each entry of the matrix gets multiplied by the real number. That's all there is to it. So those operations are fairly simple. Now, I'm going to show you on your calculator how we can check our answer with a problem like this, how we can, work with matrices a little bit on our TI-84. We're going to do this problem over again, but we're going to use our calculator this time, and we're going to show ourselves or convince ourselves we get the same answer. Okay. So let's see if we can go do that. All right, so I'm going to bring up the calculator here. And you can follow along. All right, so turn the calculator on. And the first thing we need to do after turning our calculator on is we need to go to our matrix mode. Now, our matrix mode is entered into by hitting the second key followed by the X reciprocal button. This X reciprocal button is like, it's got a little X on it with like a little exponent of -1. That's really taking the reciprocal of X. So we hit our second key followed by our X reciprocal key, which is right below your math button, because above that button it says matrix. So let's go into our matrix mode. Scroll over using your right arrow key to edit. And now we're going to stay on matrix name A and edit matrix name A by hitting enter. Now we need to configure the order of matrix A. And this matrix A was a 3 by 2. So we're going to type in 3, enter, 2, enter. And now we have to type in the entries of matrix A for the problem we just did. That'd be 1, 2, 3, 4, 5, 6. So matrix A has been entered into memory as a 3 by 2 matrix. Any questions how we did that? All right, once we enter matrix A into memory, we can get out of this mode by hitting second mode to quit. We got to go back to matrix mode, second X reciprocal button, go over to edit, but this time scroll down to matrix B. So now we're going to edit or enter in matrix B by hitting enter. Matrix B is of the order also of 3 by 2. And now we'll type in matrix B. And there's matrix B. So we loaded up both matrices A and B in memory in our calculator. Okay, so we get out of this by hitting second mode to quit. Now we're going to go back to matrix mode and we're going to select the names of these matrices so as to form the expression we evaluated. So go back to matrix mode, second X reciprocal button, stay on names this time, and select matrix name A by hitting enter. Subtract 7 times matrix B. We got to go back and get matrix B's name. Second X reciprocal, stay on names, go down to matrix B and select enter. You can also store the results of this matrix in another matrix for viewing or for some further calculations. To store this expression in another matrix, we hit our store button, which is a key right above the on button. It says STO. So I'm going to hit that button to store the results. I'm going to go back to matrix mode, second X reciprocal, stay on names and go down and select matrix name C. Hit enter. So this is going to be computed and thrown into matrix C. Hit enter, and you see the result. And does that result match up with what we've got when we work the problem out manually? Looks like it does. All right, now if you go back to matrix mode, second X reciprocal, you can see that matrix C has been configured as a 3x2. And if you want to view matrix C, you would just hit enter and hit enter again, and there's matrix C's contents. Any questions how we just did some matrix operations on the calculator?
Matrices stored.
What's that?
How do I clear the matrices?
How do you clear a matrix?
Yeah.
Okay. Well, here's one way of clearing a matrix. If you go into your memory mode, above your plus button, you see the word MEM. That's short for memory. So if you hit your second key followed by your plus button, that takes you into your memory mode here. And you can go down and if you want to reset your calculator, you would select memory management delete. Hit enter. Well, wait a minute, that's not to reset your calculator, but this is how we would go and, delete some matrices. You go into memory management and you go down to matrix here. And then you can select the matrix you want to delete. So, maybe like matrix C you want to get rid of. To delete it now, you just hit your DEL button, which is short for delete, and that will delete the matrix. Make sense?
Yeah, thank you.
Now, if you want to reset your calculator, if you like turn your calculator on and you have like Pac-Man running across your screen and you don't know what the heck's going on with your machine, sometimes you might want to reset all of the memory on your calculator. To do that is pretty simple. You go back to memory mode, so second plus button, and then you go down to reset. Hit enter, and you can reset all of your RAM, your random access memory, hit enter. And then you can either bail out at this time or literally reset your calculator, okay? I don't know if I want to reset my calculator because I don't want to erase the matrices that I put into memory here. I do have my matrices still in memory there, all right? Everybody see that there? Okay. All right. Okay, so that's for classwork number 1. Now, for classwork number 2, you can do this one here. Now, I want you to use your calculator on this one. So I don't want you to do this manually. Okay, so given matrices A and B, which are both 2x2 matrices, I want you to find -3A times plus 10B, but use your calculator to speed this up. We'll call this classwork number 2. All right, so go ahead, use your calculator. All right, well, let's take a look here. Did you, now I also worked the problem out manually here. And that would be the end result. You should get is that 2 by 2 at the end there. Did we all crank that 2 by 2 out on our calculator? Is this making sense? Did anybody get to
I got it.
it? Okay. So we know how to use our calculator a little bit to perform matrix operations. All right, now we're going to get back to matrix multiplication. Now, again, to reemphasize what must be true if we are to multiply matrices together. Well, the inner dimensions have to be the same. So the number of columns of the first matrix has got to be equal to the number of rows of the second matrix. And the resultant product matrix, its order is going to have the same number of rows as the first matrix and the same number of columns as the last matrix. Okay. So that's a requirement that the orders must be like that. All right, we're going to go to our textbook because your author does a very nice job in laying out the steps in great detail, so much more eloquently than I could ever do. And so on page 591, please do look at these examples and all these sections that I go over. Your author does a pretty good job of laying the steps out. It's only going to enhance your understanding of this course. All right. Here are some properties of matrices that I've already touched on a couple of these. Okay. Matrix addition is commutative. All right. If you add a matrix to a zero matrix, then you're going to get back the original matrix. So these are properties that matrices all enjoy. If you subtract a matrix off from itself, you're going to get the zero matrix consisting of all zero entries. And of course, in order to be able to add or subtract these matrices, they must be of the same order. Keep that in mind. All right. This is illustrating what happens, some properties involving multiplying matrices by a real number, C. I used K, but they're using C here. These are some properties that all matrices obey when being multiplied by a scalar quantity or a real number. Sometimes this real number that's being multiplied by a matrix is called a scalar quantity, S-C-A-L-A-R, scalar quantity. Okay. All right. And here's more examples, walking you through order, operations involving matrices. So please do take the time to look over some of those activities. Excuse me, those examples. All right, here's two matrices, matrix A versus matrix B. Matrix A is a 2 by 3 and matrix B is a 3 by 2. Question, can I multiply matrix A times B in that order? A times B, is it even legal? Is it possible? Well, it sure looks like it because the inner dimensions are both the same, namely 3. So we can multiply matrix A by B and the resultant product matrix would be a 2 by 2 product matrix, 2 by 2. Now, how do you actually multiply matrices together? Well, what you do to get the entries of your product matrix, you're going to take the row of the first matrix and multiply it by the column of the second matrix. So let's take a look here. So I'm going to multiply this matrix A by matrix B, and my resultant product matrix will be a 2 by 2. How do we find the 1, 1 entry, the 1, 2 entry, the 2, 1 entry, and the 2, 2 entry? That's what your author is going to illustrate now. This is on page 591 in your textbook, section 6.3, page 591. All right, to generate the 1, 1 entry of our product matrix, they're going to take row 1 of matrix A and multiply it by column 1 of matrix B. That is to say, they're going to take 2 and multiply it by -1 plus -3 times 10 plus 1 times 8. That's going to generate the 1, 1 entry of our product matrix. That's the row 1, column 1 entry of our product matrix, the 1, 1 entry. To get the 1, 2 entry of our product matrix, they take row 1 of the first matrix and multiply it by column 2 of the second matrix to generate the row 1, column 2 entry, the 1, 2 entry, by taking 2 times -6 plus -3 times 5 plus 1 times -2. To generate the 2, 1 entry of our product matrix, they're taking row 2 of matrix A and multiplying it by column 1 of matrix B That will give us the row 2, column 1 entry of our product matrix, the 2-1 entry. That's accomplished by taking -4 times -1 plus 7 times 10 plus 0 times 8. Finally, to generate the 2-2 entry of our product matrix, we take row 2 of the first matrix and multiply it by column 2 of the second matrix. That's to say -4 times -6 plus 7 times 5 plus 0 times -2. That'll be the 2-2 entry of the product matrix. When you go through the arithmetic and clean this all up, you'll see that you'll get your product matrix for matrices A and B as being this 2 by 2 over here. Questions how I multiply matrix A and B together? It's laid out on page 591 in your textbook. Is it possible to multiply matrices B and A? Do you think it's possible? Can I multiply matrices B and B times A? We were able to do A times B, but can we do B times A?
Yeah.
Well, matrix B is of what order? 3 by 2. And matrix A is of what order? 2 by what? Matrix A is 2 by, let's see here, I got this right here. 2 by 3, okay. Yeah, it's possible to multiply matrices A and B times A because the inner dimensions are the same. But what's going to be the order of B times A? Not going to be a 2 by 2 matrix. It's going to be a what? It's going to be a 3 by 3 matrix. So question, is A times B equal to B times A? What do you think? Well, A times B was of order what? 2 times 2, 2 by 2. B times A is going to be of order 3 by 3. These orders are not the same, and therefore, no. Matrix A times matrix B is not going to be equal to matrix B times matrix A. So we're finding out very quickly that matrix multiplication is not necessarily commutative. Okay? Matrix A times B is not necessarily always going to be equal to matrix B times A. So keep that in mind. Don't think that A times B is always B times A. It's not the case here. Okay. Any questions about what happened there in the textbook? There. All right, maybe we can try one here. In fact, matrix A, we will use the same matrix that we just used in the last problem there. I'm going to take matrix, here's matrix A, and then matrix B is going to be the same as it was in the last problem. But instead of doing A times B, I'm going to flip this around and do B times A. So I'm going to do B times A. So matrix B is a 2 by 3. So B times A is going to have me taking a 2 by 3 and multiplying it by matrix A, which is a 3 by 2. Is that correct? 2 by 3, 3 by 2. Wait a minute, was that the same things I set up here? 3 by matrix B is a 3 by. All right, let me double check some here. Back where we did this problem here, we did was that the same problem in our textbook? I think it is. All right. Let me go back and look at that problem in the textbook here. Was these the same matrices that they had in the textbook? No. The problem in the textbook is totally different than the one we're doing now. Okay. All right, this is matrix A and this is matrix B. All right, so can I even do matrix B times A? B being a 2x3, A being a 3x2, is that possible? Looks like these inner dimensions are the same. And so therefore it is possible. And our product matrix is going to be a 2x2. All right, it's going to be a 2x2. All right, so to generate the product, to generate the 1, 1 entry of our product matrix, we're going to take row 1 of matrix A and we're going to multiply it by column 1 of matrix B. That's to say 1 times 7 plus 2 times 5. To get the 1, 2 entry of my product matrix, I'm going to take the row 1 entry of matrix A and multiply it by the column 2 entry of matrix B. Now, it doesn't matter if you go from, if you find the 1, 1 entry, then the 1, 2 entry, blah, 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 you work this away, or you could work down by the rows first. You could find the 1, 1 entry, then the 2, 1 entry by taking row 2 of the matrix A times column 1 of matrix B. It doesn't matter. I'm going to work across this way here. So row 1 of matrix A times column 1 of matrix B is the 1, 1 entry. The 1, 2 entry is found by taking row 1 of matrix A and multiplying it by column 2 of matrix B. That's to say 1 times 6 plus 2 times 9. But what's wrong with what I'm doing? I'm not multiplying matrix B times A. I'm multiplying what? A times B. Am I not? A times B. Because I'm taking the rows of matrix A and multiplying by the columns of matrix B. So this is A times B. This is matrix A times matrix B. Where you take the row of matrix A and multiply it by the columns of matrix B. So what would be the order of my product matrix? The order of matrix A is a 3x2. Matrix B has an order of 2x3. So the inner dimensions are the same, and so therefore it is possible to multiply A times B, and therefore the product matrix will have a dimension or an order of 3x3. So my product matrix is going to be a 3x3 matrix. All right. So the 1, 1 entry again is found by taking row 1 of matrix A times column 1 of matrix B. There it is. The 1, 2 entry of my product matrix is found by taking row 1 of matrix A and multiplying it by column 2 of matrix B. Now the 1, 3 entry of my product matrix is found by taking row 1 of matrix A times column 3 of matrix B. That is to say 1 times 8 plus 2 times 7. Done with row 1, move down to row 2. Now the 2, 1 entry of my product matrix is found by taking row 2 of matrix A and multiplying it by column 1 of matrix B. That is to say 3 times 7 plus 4 times 5. The 2, 2 entry of my product matrix is found by taking row 2 of matrix A times column 2 of matrix B. 3 times 6 plus 4 times 9. The 2, 3 entry of my product matrix is found by taking row 2 of matrix A and multiplying it by column 3 of matrix B. That is to say 3 times 8 plus 4 times 7. Now we're done with row 2, move down to row 3. The 3, 1 entry of the product matrix is found by taking row 3 of matrix A and multiplying it by column 1 of matrix B. 5 times 7 plus 6 times 5. The 3, 2 entry of the product matrix is found by taking row 3 of matrix A and multiplying it by column 2 of matrix B. 5 times 6 plus 6 times 9. Finally, the 3, 3 entry of my product matrix is obtained by taking the product of the third row of matrix A and the third column of matrix B. 5 times 8 plus 6 times 7. And now we just gotta clean all these up and we'll have our 3x3 product matrix. This is gonna be 7 plus 10, which is 17. It's gonna be 6 plus 18, which is 24. 8 plus 14 is gonna be 22. 21 plus 20 is 41. 18 plus 36 is going to be 54. 24 added to 28. 52. 35 added to 30. 30 added to 54. And 40 added to 42. And that would be your 3x3 product matrix. Do we understand how we're multiplying matrices together? It's always the row of the first matrix times the column of the second matrix. All right, so ladies and gentlemen, what I want you to do is I want you to flip this around and I would like you to multiply matrix B times A now. I did A times B, you do B times A. Using the same matrices, classwork 3, I want you to find B times A. And I would like you to do the problem manually, although you can check your answer using your calculator. I would like you to do this manually and drag it out the way I dragged this one out. B times A. Okay. Go ahead and do that. Classwork number 3. Okay, now I wanted you to find B times A, correct? And let's see. B times A. And did we find that? B times A? Did anybody get that? For B times A?
Yeah.
Okay. All right. Ladies and gentlemen, I'm going to show you an example now where matrix multiplication actually has use in the real world. In fact, matrices are used for a lot of different things in our everyday lives behind the scenes. It's just that the systems in the real world are massive matrices. They're huge, a lot bigger than what we're working with here. And so for that reason, oftentimes they have to use computer systems to manipulate matrix operations. All right, here's an example of two matrices, Q and P. Let's suppose that we have two stores, store number one and store number two. I'm calling them shops, but they're the same thing as stores. Suppose that in store one, we have 162 donuts in our inventory, 34 coffee cakes, 120 hot drinks, and 44 cold drinks. In store two, we have 186 donuts, 50 coffee cakes, 145 hot drinks, and 62 cold drinks. Okay, that's the inventory of these two stores. So this is a 2 by what? A 2 by 4 matrix. Now, matrix P is a 4 by 1 matrix, 4 rows by 1 column. Sometimes we call this a 4 by 1 column vector. In linear algebra, you would call this a 4 by 1 column vector because it only has 1 column. If you have a matrix that only has 1 row in several columns, you would call it a row vector. Okay, this is a 4 by 1 column vector matrix, or just a 4 by 1 matrix that contains the unit cost of all these items. One donut costs 40 cents. A coffee cake costs $2.50. Hot drink costs $3.50. A cold drink costs $1.50 a piece. And what we're going to do is we're going to multiply these matrices together. We're going to multiply matrix Q and P together. Is it even possible to multiply Q and P together? Can I multiply Q and P together? Is that possible? Where Q is a 2 by 4 matrix and P is a what, 4 by 1? Is that possible? Looks like it's possible because the inner dimensions are the same. So our resultant product matrix is going to be a 2 by 1 matrix. So when you multiply matrix Q by P, ladies and gentlemen, you're going to generate this 2 by 1 product matrix. And that's accomplished by taking row 1 times column 1 to generate the 1, 1 product of our product matrix. That's to say 162 donuts times 40 cents a piece, plus 34 coffee cakes times $2.50 a piece, plus 120 hot drinks times $3.50 a piece, plus 44 cold drinks times $1.50 a piece, gives us $635.80. This is for store number one. So this product matrix here indicates that the 1-1 entry is the potential revenue that store number one basically has. Okay, if they sell all the items that they have in their entire inventory, they'll rake in that amount of revenue. Okay. If you take row 2 of matrix Q and multiply it by column 1 of matrix P, you generate the 2-1 entry of the product matrix. That's to say 186 times 0.40 plus 50 times 2.50 plus 145 times 3.5 plus 62 times $1.50. You'll generate $799.90 as being store number 2's revenue. Is everybody seeing this here? Do we understand how to interpret this product matrix Q and P, Q times P? This is the potential revenue of each of the two stores based on their inventory and the unit cost of each item in the inventory. Would it be possible to do P times Q? If I mix this up, is it possible to take a 4 by 1 and multiply it by a 2 by 4? Would that even be possible? No, that's not possible because the inner dimensions are not the same. So you could not even multiply P times Q. You can multiply Q times P, but not P times Q. That's not possible. So that's just a little snippet, ladies and gentlemen, where matrices can be used in the real world. And the reason why we like to cast problems in the real world in the form of a matrix is because computers are ideally suited for working with matrices. Although in computer science, they don't call them matrices, they call them arrays. Arrays. So a 2x2 array in computer science is equivalent to what we're calling a 2x2 matrix. Okay? They call them arrays in computer science. All righty. Any questions about matrix operations in that section there? Well, we're going to get out of that section now, ladies and gentlemen, and we're going to look at how to find the inverse of a matrix in section 6.4 now. And we're going to show you how we can use an inverse to solve systems of linear equations. Okay, suppose that we have a 2x2 matrix A here. Then, ladies and gentlemen, we say that this matrix here is the 2x2 identity matrix. This is called a 2x2 identity matrix, okay? And furthermore, what does this mean? Well, this means that if I take matrix A and multiply it by its 2x2 identity matrix, that's the same thing as if I multiply this 2x2 identity matrix by matrix A, and in both cases, I would get back matrix A. So the identity matrix of a square matrix is like the multiplicative identity element, in a sense that when you multiply the square matrix by the identity matrix, you get back the original matrix. Notice, to be an identity matrix, you must have ones on the main diagonal, and all the other entries must be 0. In a similar fashion, if the order of our square matrix A is a 3x3, then the multiplicative identity element for the 3x3 matrix A would be the 3x3 identity matrix, denoted notationally like this. And the 3x3 identity matrix would be this matrix here. This is called a 3x3 identity matrix, where again, you have ones on the main diagonal and zeros offset from the main diagonal. So again, if you were to multiply a 3x3 matrix A by its 3x3 identity matrix, you would get back the original matrix A. This is a well-known fact. All square matrices have an identity matrix. What's a square matrix? Anybody want to define for us what a square matrix is? I think I defined it about a week ago. A square matrix is a matrix where the number of what? Rows is equal to the number of columns. All square matrices have an identity matrix, ladies and gentlemen. But, and I'll go on with this fact here, it's true that only square matrices have an identity matrix. And so, ladies and gentlemen, non-square matrices do not have an identity matrix. Like a 2x3 matrix will not have an identity matrix. A 5x6 matrix will not have an identity matrix. It has to be a square matrix. Any questions about this here? Okay, why am I showing you this identity matrix here for a square matrix? Well, this is why. Suppose that we have a matrix A, which is an n by n matrix. If, ladies and gentlemen, there exists, this is a theorem, by the way, if there exists an n by n matrix B such that A times B is equal to B times A is equal to the n by n identity matrix. If that's the case, then we say that matrix B is the inverse of matrix A. It's an important theorem here. If A is an n by n square matrix, and if there exists an n by n matrix B such that when you multiply matrix A and B together, regardless of the order of multiplication, you get back the n by n identity matrix, then, ladies and gentlemen, we say matrix B is the inverse of matrix A. In other words, matrix A times its inverse, or the inverse of matrix A times matrix A, always gives you back the n by n identity matrix. Everybody saying that there? Here's an example. If matrix A is this 2 by 2 matrix right here, matrix B is this 2 by 2 matrix here. Fact, ladies and gentlemen, we're running out of time, so I'm not going to take the time to demonstrate this, but it can be shown that matrix A times B is equal to matrix B times A, which both in this case give you the 2 by 2 identity matrix. So matrix B is the what of matrix A? It's the inverse of matrix A. These are inverses of each other, these matrices. They're inverses. You can, put these into your calculator and dial it up and convince yourself, or multiply it out manually. Okay, but you'll convince yourself you do get the 2 by 2 identity matrix. All right, so ladies and gentlemen, do all square matrices have an inverse? The answer is no. Not all square matrices have an inverse. Those that do are called invertible matrices. They're called invertible or non-singular matrices. Those that don't have an inverse are called non-invertible matrices or singular matrices. I'm just throwing these terms out. Some of you may go onwards in mathematics and eventually get into a course where you start seeing these words surface. You'll see this like in a course of linear algebra, these terms, invertible versus non-invertible, singular versus non-singular matrices. And if you get into differential equations, you'll see also those terms pop up when you start using matrices to solve differential equations. All right, the next step is, how do we find the inverse of a n by n matrix that does have an inverse? Well, here's the procedure. Now, because this video is being recorded, ladies and gentlemen, you don't have to write this down, okay? I mean, it's on the video, it's up to you. But anyways, first of all, we take matrix, we form an augmented matrix. Where to the left of this vertical line, we have matrix A, and we have the appropriate identity matrix to the right of this vertical line. I say appropriate because if matrix A is a 2x2 matrix, this will be the 2x2 identity matrix. If A is a 3x3 matrix, this will be the 3x3 identity matrix, et cetera, et cetera. Then what we do is we utilize elementary row operations to take this augmented matrix and to transform it into this matrix, where we want the identity matrix to the left of the vertical line showing in the end, and to the right, the matrix to the right of this vertical line then will be the inverse of matrix A. That's how we find the inverse of a matrix A manually, okay? And I would like to demonstrate one here, how we can find the inverse of a matrix manually. Given matrix A here is 9, 7, 5, 4. I want to find the inverse. All right, so how do we do that? Well, first of all, we form our augmented matrix here. This is a 2x2 matrix. So our augmented matrix is going to be this right here. That's our augmented matrix. Now, ladies and gentlemen, I'm going to perform elementary row operations to get this looking like what the 2x2 identity matrix looks like to the right now. When I get done to the right, I will have my inverse matrix showing to the right over here. First, I got to make this entry become a 1. To do that, I'm going to multiply row 1 by 1/9. I'm going to multiply row 1 by 1/9 to give me a new equivalent row 1. So here we go. I put a little 1/9 out here. What's 1/9 times 9? That'll give me 1. What's 1/9 times 7? That gives me 7/9. What's 1/9 times 1? 1/9. What's 1/9 times 0? 0. There's our updated equivalent matrix after having performed that elementary row operation. Now I need to use row 1 to clear out the rest of column 1. I got to make this entry become a 0. Where am I going to get a -5 from? I'm going to multiply row 1 by -5, add it to row 2 to form a new row 2. I'm going to take -5 times row 1 plus row 2 to form a new row 2. So what am I going to do now? I'm going to take -5 times row 1. And what's -5 times 1? -5. -5 times 7/9 is -35/9. Don't turn these into decimals, leave them as fractions. -5 times 1/9 is -5/9. -5 times 0 is 0. And to this, I'm going to add row 2. This will form a new row 2. It's going to form a new row 2. So I took -5 times row 1's entries, and to that I'm going to add rows 2 entries to form a new row 2. -5 plus 5 is 0. -5 35/9 plus 4, 4 being another name for 36/9, is going to be -35/9 plus 36/9 is 1/9. -5/9 plus 0 is -5/9. 0 plus 1 is 1. There's your new row 2. Let's update our matrix. Now I need to make the 2/2 entry become a 1. To do that, I'm going to multiply row 2 by 9 to form a new row 2. Row 2 gets multiplied by 9 to form a new row 2. What's 9 times 0? 0. What's 9 times 1/9? 1. 9 times -5/9. -5. 9 times 1. 9. There's our new updated matrix. Now I'm going to make this 1/2 entry become a 0. Because remember, I'm trying to make this matrix to the left look like my 2x2 identity matrix. So where do I get -7/9 to add to row 1 to make this go to 0? Well, I'm going to multiply row 2 by -7/9. Add it to row 1 to form a new row 1. I'm going to take -7/9 times row 2. -7/9 times 0 is 0. -7/9 times 1, -7/9. -7/9 times 5 is going to be 35/9. -7/9 times 9 is -7. To that, I'm going to add row 1. To form a new row 1. This gives me 36/9, which is 4. This adds up to -7. There's my new equivalent row 1. I will update the matrix down here. So my new equivalent row 1 is this right here. And row 2 gets penciled in from the previous matrix. We're done. Ladies and gentlemen, this matrix is the 2x2 identity matrix. Now, therefore, this matrix to the right of the vertical line is the inverse of matrix A. That's the inverse. So we found the inverse of matrix A by using elementary row operations. There you go. And it's nice to have this on a recording so that you can go back at your leisure and maybe run this over and over again to see exactly what just happened there. Got to press for time. I'm going to show you now, ladies and gentlemen, an easier way to find the inverse. Now, this only works for 2x2 matrices. Shortcut. Only for 2x2 matrices. It does not work for 3x3 or 4x4 or 5x5 or 6x6, etc., matrices, only for 2x2 matrices. Suppose that I have a 2x2 matrix here. Those are the entries of my 2x2 matrix. To find the inverse matrix, you can use this shortcut, unless I specifically want you to demonstrate this method. Okay, so make sure you do understand this method, how this works. I may have you demonstrate a 2x2. All right, to find the inverse of a 2x2, there's a shortcut. All it is 1 over A times D minus B times C times this 2x2 matrix, which is going to take my original 2x2 matrix and interchange these values. And then these values take on the opposite sign. That's the shortcut for finding the inverse of a 2x2 matrix. Everybody see that there? So I can show you how this shortcut works for the matrix we just got done finding the inverse for by using elementary row operations. I'm going to show you how to get this inverse only using this shortcut here. So here we go. The inverse of matrix A is 1 over 9 times 4 minus 7 times 5. Careful your signs. Times this matrix where these entries get switched. These entries take on the opposite sign. Therefore, this is going to be 1 over, this is 36 minus 35, which is 1. Ladies and gentlemen, you are looking at your inverse matrix. This is your inverse matrix. Okay, 1 times this is this. That's the same matrix we got right here by using elementary row operations. You understand that there? That's a shortcut. That method only works, that shortcut only works for 2x2 matrices though. Don't try to use it with a 3x3 or 4x4. It's not going to work. All right, time check. All right. Now, how can we find the inverse of a matrix using our calculator? Because there will be times, like when I'll let you use your calculator for finding the inverse. Let's just do it again for matrix A here, but this time let's use our calculator. So bring up the machine. Where is my, what just happened here? Hold on a second. There's my calculator. Let me show you how to find the inverse of a square matrix on the calculator. Nice thing about the calculator is it'll find the inverse of any square matrix if it has an inverse. It may not be in an invertible matrix. It may not possess an inverse. All right. So let's go to matrix mode, go over to edit, and let's type in that 2 by 2 matrix we just found the inverse for. So 9, 7, 5, 4. We're going to show you how you can find the inverse of this matrix using your calculator. Once you enter in your square matrix, get out of matrix editing mode, second mode to quit. Now, ladies and gentlemen, you got to go back to matrix mode. Second X reciprocal button, select, stay on names, select matrix name A, and now you're going to hit your X reciprocal button. This is how you're going to find the inverse of matrix A. Hit enter, and boom, you got the inverse of matrix A. There it is. I've shown you 3 ways of finding the inverse of that 2 by 2 matrix. The first way was using elementary row operations. The second method was the shortcut. And the third method was using your calculator. Any questions? How we found the inverse of that 2 by 2 matrix? I don't, what's that?
Could you, okay, so could you use the calculator for anything else except a 2 by 2?
It could be a 3 by 3 matrix or a 4 by 4. As long as those matrices are invertible, as long as they have an inverse, the calculator will find it, okay?
So if it doesn't have an inverse, it'll just come up as like error or something.
Yeah, it's gonna come up with like an error, all right? See, the only way a square matrix does not have an inverse is if its determinant is equal to 0. We haven't talked about determinants yet, all right? We're going to in the future. But not all square matrices are invertible or have an inverse. It will come up as an error, all righty? But any other square matrix that has an inverse, your calculator, as long as you type it in and, just type in the name of the matrix and hit your X reciprocal button, you'll get the inverse of the matrix. And ladies and gentlemen, if your matrix does not, if it comes up with like decimal entries and you want to convert them into like fractions, all you got to do is hit your math button and select the frac function, and then it'll convert all decimals into fractions. Okay, I don't have that problem with this matrix as they are integers, but I'm saying some inverses have messy decimals. It happens, okay? To turn them into fractions, you just, with your matrix showing with the messy decimals, hit your math button, select frac, hit enter. It'll convert all the decimals into fractions. Ready? Okay, one last thing here to wrap up this session here. We're going to show you, ladies and gentlemen, how to perform what is called matrix algebra to solve a matrix equation, which will be used to solve a system of linear equations. Suppose I have this square matrix, matrix A here, which is going to represent the coefficients of the system of 2 linear equations and 2 unknowns. Suppose I have a system of 2 linear equations, 2 unknowns, and I want to solve it. I'm going to show you a new method. It's called the matrix inversion method for solving a system of linear equations. Matrix inversion method. First of all, we define the square matrix A to contain the left-hand side coefficients of our equations. So matrix A will consist of this coefficient, this one, and this one. Then we're going to have a matrix X, which will be a column vector matrix that will contain all the variables in our system. Our variables are just X and Y. That's a 2 by 1 column vector. Matrix B is going to be a 2 by 1 column vector that will contain the right-hand side constants of this system, C and F. Now, ladies and gentlemen, would you believe that I can cast the system of 2 linear equations and 2 unknowns in the form of a matrix equation? Specifically, matrix A times matrix X is equal to matrix B. This is called a matrix equation. All these are matrices. Now, how would I solve for X? How would I solve for the X and Y coordinates of this ordered period of this system of two linear equations, two unknowns? Well, I got to get rid of the matrix A. And what's going to get rid of matrix A? I would have to multiply matrix A by what to get the 2 by 2 identity matrix? I would have to multiply this matrix by its inverse. So I'm going to have to multiply both sides of this equation by the inverse of matrix A. Got to multiply the right side of the equation by the inverse of matrix A. And notice the order of multiplication on the right side. It's the inverse times matrix B. When you multiply, ladies and gentlemen, a square matrix by its inverse, you always get the identity matrix. So this is going to be the 2 by 2 identity matrix. But what's the 2 by 2 identity matrix multiplied by a 2 by 1 column vector? That's going to give me a 2 by 1 column vector, which is just going to be X. So this is just going to be X. And ladies and gentlemen, you are seeing how you're going to get your ordered pair solution for this system of linear equations. X, which contains the X coordinate and the Y coordinate, is going to be equal to the product of the coefficient matrices inverse times the matrix B. This technique is called matrix inversion for solving a system of linear equations. And I'm going to demonstrate one now, as it's 2:04. Any questions about what's going on here? It's called a matrix inversion method for solving a system of linear equations. It calls it the matrix inversion method because when you find the inverse of your coefficient matrix, you're inverting the matrix. To invert the matrix A means to find the inverse of matrix A. And that's what we need to ultimately solve this system of equations using matrices. That's why they call it matrix inversion. Okay. All right, so let's put it to work. Let's see if we can, utilize this matrix inversion technique to solve a system of two linear equations and two unknowns. And here is our system of two linear equations and two unknowns. And I want to solve this system for its ordered pair solution, if it even has a solution, by using matrix inversion. How do we do it? Well, first of all, matrix A is going to be our coefficient matrix, which is going to consist of 5, -3, 10, -7. Matrix X is going to be the 2 by 1 matrix that contains the X and the Y variables. Matrix B is going to be a 2 by 1 column vector matrix that will contain the right-hand side constants of this system. All right, here we go. Now, how are we going to solve for the X and the Y coordinates of our ordered pair solution to this system? We're going to use the result of having solved that matrix equation on the previous slide. X is going to be equal to the inverse of matrix A times matrix B. This is how we're going to get the solution. So matrix X is going to be XY, which is going to be equal to the inverse of matrix A. Now, what is the inverse of matrix A? There's 3 ways you can find this inverse, like I indicated. You could use elementary row operations, of which we don't have time to do. Or we could use the shortcut method to find the inverse, or we could just put this into our calculator to find the inverse of this matrix. Ladies and gentlemen, I got to speed things up, so I'm going to have to use my calculator to find this inverse. So let's go to our calculator and type in that 2 by 2 matrix and find its inverse. So we're a little cut for time here, so I'm going to have to use the calculator to speed things up. All right, so let's go to matrix, edit, 2 by 2, matrix A for this system is going to go in as 5, -3, 10, -7. Second mode to quit. Go back to matrix and bring up the name matrix A. Hit your X reciprocal button. Ladies and gentlemen, hit enter. There's the inverse of matrix A. There it is. Notice we have messy decimals. We can clean this up. We can turn those decimals into fractions. Easy thing to do. Just hit your math button. Select the frac function, number 1, enter. Enter. Decimals are converted to fractions. There's the inverse of the coefficient matrix A. I'm going to write that down on my paper. All right, now here we go. My 2x1 column vector is going to be my solution, and it's going to be found by taking the inverse of matrix A and multiplying it by matrix B. Now this is a 2x2 matrix being multiplied by a 2x1. We can do it. Inner dimensions are the same. And what's going to be the dimension of my product matrix? It's going to be a 2x1. Makes sense, because that's what this is, a 2x1. Everybody see that there? So, in order to get our solution, our 1-1 entry, we take row 1 of the first matrix and multiply it by column 1 of the second matrix. So 7/5 times -20 plus -3/5 times -50. To get the 2-1 entry of my product matrix, I take row 2 times column 1. 2 times -20 plus -1 times -50. What's 7/5 times -20? That's going to be -28. What's -3/5 times -50? That's going to be 30. What's 2 times -20? Plus 50. Ladies and gentlemen, we're about to crank out our solution here. So my x coordinate of my ordered pair solution is going to be 2, and my y coordinate is going to be 10. We're done. The ordered pair solution is 210. X coordinate is equal to 2. Y coordinate is equal to 10. This is called matrix inversion for solving a system of linear equations. But to do so, we always have to find the inverse of our coefficient matrix of the system. Now, could we have done this on our calculator to speed all this up? Because I did multiply these matrices together manually. The answer is yes. Let's go back and convince ourselves that we could also have done this on our calculator to get the result. Remember, matrix A I already entered into memory. Matrix B I did not enter, and I got to go to back to matrix, name at matrix, edit, go down, wait a minute, wrong. I got to go back to matrix, edit, go down to matrix B, now enter in matrix B, which is just a what, a 2x1. Matrix B is -20. Hold on a second. -20 and then -50. That's matrix B. Second mode to quit. Now we can have our calculator do this. All you gotta do is go back to matrix, select matrix name A, find its inverse, and then multiply that by matrix B. Second matrix, matrix B, enter, boom. There's your solution, your ordered pair solution to this system, 210. This is called matrix inversion. Now, for a silly little system of 2 equations and 2 unknowns, ladies and gentlemen, you know, you probably don't have to use matrix inversion. I mean, you could probably just solve this system, you know, all the other ways we showed you. Graphing method, substitution, elimination method, okay? So where would this become advantageous? Well, I'll tell you where it becomes important. Out in industry, matrices usually are huge, okay? Usually the matrices are like thousands and thousands of rows by thousands and thousands of columns. Massive matrices. Well, for humans to operate on those matrices and to find the inverse is virtually impossible. Can't happen. So you have to turn it over to a computer system. All right, computers are ideally suited for working with matrices. They're called arrays. All right, so once you can cast a problem in the form of an array or a matrix, then you can take advantage of the speed of a computer system to solve the system within a fraction of 1 second, as opposed to 20 years it would take for a human to do that. Okay, so I'm just showing you how the dynamics work for very small systems here. These dynamics would extrapolate to larger systems. All right. Systems of 3 equations and 3 unknowns, 4 equations and 4 unknowns, 5 equations, 5 unknowns, 10 equations, 10 unknowns. I'm showing you how it works because it would work the same way. It's just that you'd have tons more calculations to undertake. So does this matrix inversion method make any sense here? What just happened there? All right. All right, last class work, ladies and gentlemen. I want you to, using your calculator, you guys got a bonus. My face-to-face section did not have time for this last class work. You guys get more for your money. Lucky you. Solve by matrix inversion using TI-84. Here's the system. It won't take long if you use your calculator. If you do this manually using matrix inversion, it's going to take a longer time. There you go. I want you to solve this system of 2 linear equations, 2 unknowns by using the matrix inversion method. I will give you a jump start. Matrix A is the coefficient matrix of the left-hand side coefficients of the system. Matrix X is our column vector consisting of the variables of the system. Matrix B is a column vector consisting of the right-hand side constants. To solve this system, all you got to do is find the inverse of matrix A and multiply that by matrix B. You're going to let your calculator take care of this. You guys go ahead, dial it into your calculator and solve that system for me using matrix inversion. Okay, ladies and gentlemen, I'm gonna kind of walk through the calculator so you can check your answer here. I'm gonna bring up the calculator. I'm just gonna walk through this problem here and you can kind of check and see if that's what you got and critique me. Let me know if I'm doing it correctly here. All right, here we go. First of all, I'm gonna enter in matrix A. Two by two, which is 3, 7, 4, 9. Matrix A is entered into memory. Done. Second mode to quit. Go back to matrix. Go over to edit. Go down to matrix B. Enter. Matrix B is a 2 by 1. Let's enter in matrix B, which is -5, -7 for this system. Matrix B is now in memory. Done with that. Second mode to quit. Now we can perform the multiplication of the inverse of matrix, the inverse of matrix A and matrix B. Here we go. So second matrix. Stay on name, select matrix name A, take its inverse by hitting X reciprocal. Times, you got to go back and get matrix B. Back to matrix mode. Stay on names, go down to matrix B, hit enter. Now you got matrix B, hit enter, ladies and gentlemen, and this should be your ordered pair solution to the system if it has a solution. And -4, 1. Did anybody get that?
Yeah.
Yeah.
All right, that's called matrix inversion for solving a system of linear equations. And the beautiful thing about this method is it would work for massive or large systems, not just small systems. It's just that you'd have to, do a little bit more data entry and typing in larger matrices. But your calculator would be able to solve it in about the same time that it solved the system of 2 equations, 2 unknowns, within a fraction of about 1 second. Okay, that's called matrix inversion. All right, that's it. That's all I got, ladies and gentlemen. Again, if you haven't done the exam, it's open till midnight tomorrow night. Try to get that done. And in 1 week, I will make available the chapter 6 Alex exam. And is there a chapter 6 quiz I have to open up to or something? I think that's coming up pretty soon when I'll have to open up the chapter 6 Alex quiz. But that is it. And of course, the chapter 6 homework, I'll make sure is updated on Alex and open for you to do. Okay. Well, you have a safe Easter, and hopefully I'll see you next week. If you don't have any other questions, take care. I'll stay on the line for a couple minutes if you have any questions.
Happy Easter.
Yeah, same to you.